Right, let's have a little look at a few little things for this little section on Pascal's triangle and the binomial theorem. The first thing to say is here's Pascal's triangle. It's very easy to draw. Basically, there it is there, and it doesn't take a moment to draw down to the respective line you want. This is often called, I would call this the fourth row, and I would call this the fifth row. So by that reasoning then, this would be the third row, the second row, the first row. So this is the zeroth row. And they correspond to the powers and in the expansion of a bracket. So this would be the fifth power. The zeroth power is 1, of course, and then you carry on down. And it's the expansion of 1 plus x to the n. So here's the expansion. So suppose I was using Pascal's triangle to do 1 plus x to the n cubed. Let's just do it quickly here. 1 plus x cubed equals. Now what does that equal? Well, to do it quickly, you just do 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And that would equal, then what you do is you take the first term and you descend in powers in this direction. So you start from the highest power, which is the 3, and then you go 1 squared, 1 to the 1, and it descends in powers. You see that direction? When you do exactly the same with the second term, here it's plus x, so it'll be plus x cubed, plus x squared, plus x to the 1, and you've descended in powers in the reverse direction. And then all you need to work out the actual answer is you combine them like so. There's 4 terms here, isn't there? Aren't there? So what do we get? Let's have a look. So that would equal then, what do we get? The first term, 1 cubed times 1 is just 1. Then you've got all these 1s to a power just 1, so we can just not worry about them too much. So that's 3x with a plus, and then this would be 3x squared now when you combine all those together in a product, and then 1 times x cubed is just x cubed. There we go. So it's a very easy way of expanding brackets. So the Pascal's triangle essentially are the terms in the binomial, give the terms, the numbers in the binomial theorem that correspond to the answer. So that's how you'd use it in practice here, and oftentimes you write Pascal's triangle because it's a quicker method to generate these terms from the binomial theorem. So there we are. So with that thought in mind, you see, it's very easy to just write down an expansion. So I'll do another one, but this time I'll do something slightly more difficult. Let's do a plus b to the 4. Well, I can write that down as a to the 4 plus a 4 a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4. And that was the reason I could write that down so quickly, was because you can just spot it how it goes from Pascal's triangle. In practice, though, you generally take a few moments longer than that to minimize the likelihood of making a mistake. So what you would do is you'd go down to the next row here, to the 4th row, and that's where you get 1, 4, 6, 4, 1 from. And then here the first term descends in powers, so you know the highest one would be 4, then cubed, then squared, then single power, then none of them. And then you do the reverse direction, so you go with the second term plus b, it's b to the 4, b cubed, b squared, b. Now it gets a bit tricky when you get numbers, you know, combinations of, so to speak. So if this was 2a plus 3b, say, to the power of 4, then of course you're not going to be able to just rattle it off very, very easily without perhaps making a mistake. So perhaps we could do that one just quickly, just to show you how easy it is. So 2a plus 3b to the 4 then. Let's have a go at that one. Well, let's draw Pascal's triangle. It doesn't take a moment to do, as I say. And here's the 4th row that we wanted, 1, 4, 6, 4, 1. The first term is 2a, and you descend the powers. Because it's not just a single object, there's 2 lots of a, and you've got powers flying around. Wrap it in a bracket so you don't make a mistake. And then it's 2a cubed, 2a squared, and as I say, it doesn't take long to do this, and 2a. And then the reverse direction is plus 3b. So you'd have 3b in a bracket to the 4, and then 3b in a bracket cubed, and then 3b bracket squared, and then 3b, and none of them. Okay, so there's your terms. So it's just simply a matter of combining them then and not making a mistake here. So you're going to get 5 terms generated from the bracket, yeah? So for example then, 3b to the 4, well that will be 3b times itself 4 times. So coming out from that will be 3 times 3 times 3 times 3, and a b to the 4 as well. So that would times 1, so that would end up being 81b to the 4, for example. Let's do the middle one just to illustrate it here. 2a times 2a, there's a 4 coming out as a number. 6 4s are 24. But you've also got 9 here. See it? 3 squared comes out here, so that's 9. Oh, we'll do that, make it easier on ourselves. 9 6s are 54. And then there's a 4 here. 54 times 4 is 216. So you'd get all the numbers out first. Then the number of a's, well there's the a squared, that's the only time it happens. And then the b is b squared here as well. So there's that term there. And if you go back to the 2a to the 4 at the first one then, you could write that one out. You'd get 2 to the power 4, which is 16, times the a to the 4 times 1. So that's what you get. So I hope you can see that it's fairly easy to use, straightforward. You just draw your grid in your template and everything will work out from that. So that's how you would do it. And again, if there's a minus here, then you'd carry the minus with the 3b when you write down all those bracketed terms. So now the formula wise then, if we were writing it, the formula, let's just write out the formulas then for these terms, because we can also use these, and on occasion it's more convenient to use them. So here you've got NC0, I'll get a different pen. So you've got NC0 times plus NC1 times x plus NC2 times x squared plus dot 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 all the way up to NCN times x to the n. There's the formula. Here's the formula for NCR in general. So, and more customarily, we write this out as 1 plus n x plus n minus 1. This is what we write down often in practice. X squared over 2 factorial plus n minus 1 n minus 2 x cubed over 3 factorial plus dot 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 and so on. So there's what we use in practice. So if you're told that the coefficient of x squared term is 3 times the coefficient of x, you take the numbers involved here and the numbers there, write them down, what they equate to, and solve for n. So that's a typical question where you'd prefer to use this formula here. The a plus x to the n is just a slight modification of this here. Instead of the going up in powers of x to the n, the an's are also come into being here. So let's just write that down. So we start with an and nc0 plus a to the n minus 1 nc1. You generally write it around the other way, sorry. Let me just do that, because it's easy to remember this way. So again, it would be nc0, and it would be a to the n plus nc1, and it would be a to the n minus 1 times x, plus, and I hope you can see how that generates itself, nc2, an minus 2 x squared, and so on. And so you can see that that just slightly gets modified by descending powers of a's as well as you go along here, from a to the n minus 1, and so on, just as we did in Pascal's triangle, essentially. So I think that's all I want to say at the moment. As I say, if I think of anything other things that I want to include in this section, I'll put it on the long click. But otherwise, I think that's good enough to get started. And we'll probably start, for the most part, with just using Pascal's triangle and generating expansion of these brackets. Okay then, great.